right, we have made it to the last lecture. So today we are going to do a final review. I'll make some comments on the homework 5 regarding providing. There's a couple hiccups with provide, but I assume it's going to be ready now or ready soon, very soon anyway. What we're doing is we're making it so that we can easily test your program on multiple different files, databases, and so I'll show you how to set that up. It's relatively easy to do, to tell you the truth. Let's see. Then we will talk about all this other stuff for the final. So well, I'll make some comments on the final in a few minutes. But then we'll go over. So on the first day, I don't know if you remember, we did we put some data into, or I showed you some data regarding some various containers that might be like so far back in your brain that you don't even remember it at that point. At this point, that's all right. But I'll refresh your memory, and then we'll see if we can now analyze it a little better, having come this far. And then I just comment a little bit on some future data structures. Okay? Questions before I begin regarding homework, test. Oh, final exam. I guess I made the assumption it was going to be in here. I don't know that that's the case yet. I will post that when I find out. I've asked the head office at CS where it's going to be, and we don't know yet. Or maybe we do. I don't know. Yeah, Hobby. Oh, the web portion of the homework. It hasn't been posted. Busy doing other stuff. OK, well, maybe not right now. But we can. It's not required for your assignment, certainly, of course. But we'll see what we can do with that. Other questions? Yes, Remy. Could I make the font size bigger? Not on this one right now. I can't. But I can't right now. No, I don't think so. Sorry. Yes.
If we want to take the final on Wednesday, do we need to let you know?
Nope. You can take it whichever day you want. Yep. Question. Same as before. You get a cheat sheet, 1 page back and front, handwritten, etc. Let's see. What else can I say about the final right now? Well, like I said, I was going to comment on it, but I might as well make comments now. I plan on making it 95% of the material being what we covered since the mid-year. So it's not like you have to go back and relearn how to balance AVL trees, although to a first order approximation you should be able to do that. Or you didn't really retain the knowledge before. But I'm not going to go and ask the same types of questions before. I'm going to ask questions that are related to the stuff we've done since the mid-year. Vivek.
So this is going to be like the full 2 hours?
It's still going to be the full time, yes. It's just I don't know if it'll take that long. I'm not going to make it extra long to take up the space. It'll probably be roughly the same size as the mid-year. And I plan on counting it about the same as the mid-year too. Although, as I said before, if you did poorly on the mid-year and you do much better on this exam, I will weight this one more heavily. So that's that. Other questions about the final? No? OK. Let's see. Before I talk about getting your main working for the homework, I appreciate you guys' hard work on this. I know there were a zillion people in here this weekend, and people were still working on this assignment. Hopefully you saw my Piazza post kind of geared towards people who at this point are like, I'm not sure I'm going to finish. We will do the best to grade your assignment based on the work that you completed. In other words, how much you got done, we will try to give you a grade on that. If it doesn't compile and it doesn't actually do anything, well, we got to dig into the code, and I'm not necessarily sure we'll be able to figure out what you were trying to do unless your comments are really good and your README file is really good. However, if you can make it do something, there's another part of the Piazza post that says, look, if you can make it print out a word or print out the song titles where the word occurs, well, that'll get you a lot of points, because that's 70% or 60% of the problem, right? So if you can get it that far, then terrific. And if you can't finish it, provide what you've got and try to comment as much as possible about what you think you were trying to do anyway. Make sense? I didn't expect everybody to be able to do this perfectly, this assignment. So for what it's worth, there's a certain portion that that I expected to not necessarily be able to do the whole assignment. This was the hardest assignment you've had in here, and it's to be expected that some of you guys won't quite figure it out. Programming is hard. Trust me, finding bugs is hard, and I've said that the whole year. It's a tricky thing to do, especially given a deadline. Other questions on that or comments? Yes?
On the example output you could give us on the homework sheet.
On the example output on the homework sheet, yes.
Do we have to follow that exactly?
Well, okay, you have to follow the examples. The example on the homework had some it had some missing parts, right?
Yeah,
but you should.
Also, reprinted the artist.
Yes, you reprint the artist and title exactly like that. So see the output on the Piazza post that some people have fixed from my original output. But that's the way it should do. And you should be able to type angle bracket break before, to stop the program from running as well. Yeah. Okay. Anything else on that? All right. Okay, so let me show you. Sorry, Remy, this font's really small. I'll try to blast this up a little bit for here. In your main program, here's what we're going to do. Okay, we are going to have it so that you can input your command line arguments. And that's what this little part of main does. I've had this up here before, and people have asked questions about it. But what this says is, this says how many command line arguments are there, including the file name, which happens to be the first command line argument, even though it's not really an argument. But if you want to know the file name, that's the first one. This is just an integer of how many there are. This is a pointer to an array, basically a character array, basically strings, a pointer to char strings of the input file names. Okay, I'll show you what I mean in a minute on the command line. And what you can do is you can check to see if there are two of them. In other words, the file name and the name of your lyrics database that we're going to ask you for. And then you just pass it in here instead of creating your own file name. Okay, that's it. Those are the only changes you have to make it work with our provide script correctly. This guy, and then you can check to see if there's two. You don't even have to do that. If you don't, you'll get a warning saying you haven't used this variable. And then you put the argv1, meaning the first argument after the file name, and that's the actual file name string. Questions on that? I'll post this on Piazza as well, so you can see the example, but it's relatively straightforward when it comes down to it. Let me show you what I mean here. Okay, so this is the same thing here. Here's the int argc, a character pointer to a bunch of strings, which are the arguments, and then the actual first argument, the argument in the first index is the name of your file. So how does that work? Well, let's see, song search, and then I happen to have a poems.txt file that Bruce came up with, right? And that says, look, this is the first string in the index of your, the first index string of your command line argument. Song search poem.txt, and then it reads in your poems, and I'm not sure what words are in your pebble is in there, right? So, boom. All right, and then it should print end of report after each one. Yes, Laura.
Should we have in the code that you put whether scale at every 10,000 seconds?
Good question. Should you undo that? You should. Sorry, break. You should take that out in the following way. The 10,000 is for your own. That's for your own debugging. When you submit it, see how this is false here? That was true in the read lyrics. That should be false, and that will ignore that debugging line if you want. And it shouldn't do that. If it does, and as long as it passes the Piazza, not the Piazza, as long as it passes the provide thing, it will be submitted. But you'll make us do extra work if it says failed the test, which is just basically a very easy test like this one. We're gonna basically do that with your program and see if you can find the word pebble, for instance. Okay. Does that answer your question, Mo? Okay. Other questions on that? Yeah, Marcus.
So if the provide script checks it against expected output, and we resolve our ties differently from the way
Yeah, good question. I don't believe we'll be testing any things that have ties for the provide script. Yeah, so that won't be an issue. Yeah, good question. Yes. Yeah.
Should you build your program to take only one command line?
Yes. So you don't. If it takes more, that's fine. But just this first one's one we're going to look at.
Okay.
Yeah. I mean, I just happened to in this one, so I could get rid of that warning. and to check and just make sure, hey, it doesn't exist. But as I said, I'll put that example on Piazza this morning. Okay. Other questions? Okay, awesome. All right, so back to the stuff. Quick review on stuff that we covered since the mid-year. Okay, heaps. Covered heaps. And remember, heaps were used for priority queues because they happen to give us the best asymptotic behavior for priority queues. In most cases, if you have enough time and you want to set up an ordered list, it's going to take you a lot at the beginning, but then you are going to get great remove min and min element behavior. So again, it depends on your use case for this stuff, right? But a heap is pretty good all around, right? Inserting is log n. Min elements just order 1, it just pops it right off, right? And then I guess it has to bubble up, but or bubble down rather. But and then remove, or no, not sorry. For min element, it just returns it. For remove min, it has to remove the first element and then bubble. Remember, well, we'll do an example, but put the end element into the root and then bubble it down, and that's in log n behavior. So overall, heaps are pretty good for this. Okay, we can also use it to do a very fast sort with our heap sort. Not as good as some other ones, but pretty good overall. Okay. Remember, heaps have this idea or have this property that the priority of their key of the parent is greater than the key of their children, however you define greater. For a min heap, it's actually less than in the sense of your children are greater than you, right? And that's true for each one. For a max heap, it's the exact opposite. There is no implied ordering. A whole bunch of people I talked to, we went back and forth about whether or not it's a good idea to try to use a heap in the song search. And some people, I think, figured it out. But people were trying to do things like, well, keep the top 10 here. Well, that's a little tricky. You could probably do it with a max heap if you're just taking off the top one here. But you've got to be a little careful about it because you only get access to one end of a heap, right? You get the min element or the max element, depending on which kind of heap you're doing. You get the access to one element. And that's, again, what makes it kind of fast. Okay, that's what the heaps are all about. Okay. And remember, heaps are binary or complete binary trees, right? You got to fill them left to right until the end. The only ones that can be empty are the leaves, right? And you fill those left to right. Go along. Okay. Remember that heaps have this nice little, if you put them in an array, they've got these nice little mathematical properties, which means you don't have to store them as nodes anymore. You can just store them in an array, and the mathematical operations, a little bit of arithmetic, gives you your children and your parents, right? And that's very nice. We generally, because of it makes it a little easier, leave the first element out, right? We leave the first element out, and then we have everything else fill in here, and it works out just fine for a complete binary tree. Okay? If you need this row or this set of nodes to have children, you're going to have to expand your tree by double, because that'll double the number of children you have there. So you need to do that. But that's how we're going to keep them in line. This is something you might want to write down on your little cheat sheet, right? I might ask you, who's the parent of element 12 or whatever, right? And if you wanted, you could draw it all out, or you could just use your little mathematical formulas. Okay. All right. So here's some example problems that we would do. So for the heap shown to the right, perform remove min. All right. So 5, 10, 8, and 12, 11, and 14, 13, and 22, 43. All right. If I want to remove min, how do I do it? Ideas? Because maybe you just know this. If I want to remove this one, how do I do it? View? Okay, 5 goes away and gets returned, hopefully. And then?
When you pick whichever one of its children, those direct children is the smallest.
Is that what we do? I don't think that's what we do for the heaps. Allison?
Take the last element.
Take the last element and put it right up here, right? And then bubble it down. That leaves this one empty, which is kind of what we wanted. We wanted the last one to be gone, right? And then you have to bubble it down, which means now you check the ones versus which ones are, which of its children is smaller in this case. This is a min heap. 43 and 8 switch. 8 and 43. And then this one still gets bubbled down, and 13 and 43 end up switching. Right? 13 and 43, and there we go. Questions on that? How quickly we forget some of these things, right? We can have to go refresh your memory on some of these. All right, so that's that one. And let's see, 43, 5, 8, 13, I believe. OK. Describe the procedure to add a new element to the heap. How are we going to add an element to this? Let's say we add 6 to this heap. How are we going to do it? Yeah.
Put it in the first, left from 11.
Left from the first empty spot. Good. And then you just bubble it up, right? Which means look at a parent and see if you need to swap. In this case, you do. 6 and 11. And then look at this one's parent and see if you need to swap. And you do. 6 and 10. And then look at this guy, this one's parent, and you do not need to swap, and we're done. OK, the bubble up in that case. Logarithmic behavior, not too tricky, but it's you got to remember how to do it. OK, what I think I'll try to do is give you space to write this, so you don't. I want you to be able to describe it, and I don't want you to just. Remember in the AVL tree there were lots of answers, and then I couldn't really tell what your algorithm was. I'll try to make it so this works a little better. Okay, and remember it still meets the heap requirement of the child. In this case, is less than, or the parent is less than both of its children. Okay, that'll always work for these. Okay, all right. I said add 6. Describe the procedure to add a new element. So I might just ask you to describe it, which is exactly what you'd say. You'd say replace the last, or add an element to the last place in the first unused spot, and then bubble it up, and that's all you need to do. And bubbling it up, check with your parent, et cetera, et cetera. Okay. Question on heaps. No? All right. Let's go on. We talked a lot about sorting, right? And you guys have been explaining your sorting algorithms recently over the last few days in lecture. Has that been going all right? People have been relatively, I know there have been some hiccups here and there, but have people been relatively happy with the in-person grading? Don't see too many no's. OK, that's good. I'll take a look. I'll talk to the TAs and see what they thought too. But I think for the most part, the people I talked to, you guys have for the most part done great on the in-person grading. So that's good. All right, so we covered lots of different sorts, right? Insertion sort, selection sorts, heap sorts, shell sorts, merge sorts, quick sorts, and radix sorts. Those are the ones that we actually went over the discussion, went over them in class. And I will not ask you any other kinds of sorts, right? I won't throw in a crazy new one for you, right? But you need to be able to discuss these, kind of like what you were doing for your homework, right? Now, I know that some of you guys didn't do shell sort, right? Well, you should at least go back and remember, oh, there's going to be these gap sizes, and you have to, it's kind of like insertion sort, except that you do it by gaps first, and the gaps get smaller, et cetera, right? I would say quick sort's probably the one I'm going to focus more on, right? I might throw in a question about radix sort, but it's not your typical sort because it's not a comparison sort. Right? So be able to describe the algorithm, explain the complexity for the best and worst cases. And by explain, I don't mean derive, obviously. I mean just talk about it and say, look, if for insertion sort, there's a certain way that you can, if you order them, if they're already sorted, well, insertion sort doesn't need to do much. It needs to walk through the list once, and so that's order n behavior, right? Selection sort, right? There's no way to get around the fact that selection sort's order n squared. It's not going to happen. Okay, things like that. Okay, I think you guys have had lots of practice on the sorting lately. Okay. All right, so some of the key ideas about sorting. Most sorts are comparison sorts, right? The ones where you compare two elements together and say, move one or both to a different location, that's a comparison sort. We can get order n log n behavior if we have a divide and conquer scheme, right? It's the dividing and the conquering part that says, hey, if you break it into pieces, well, you're going to increase your ability to sort faster, and therefore we can get to log n time. You can't get to order log n time itself. The best you can ever do is for a selection or for a comparison sort is n log n. Can't do any better than that. All right. Some sorts can do better in the sense that they aren't comparison sorts, like radix sort has a different behavior, right? It's better than n log n in the sense that, oh, it doesn't do that, but it's hard to compare them, right? There's lots of overhead to doing a radix sort. You have to figure out what the actual position is, and that takes some time, and that ends up, in many cases, outweighing the fact that you're using this different type of sort. So you can't really compare them necessarily, but you can still talk about in terms of the behavior based on the number of operations you have to do. Okay? Remember, sorting can be in place. Sorting can be not in place, where you have to keep creating more structures as you go along to store the data. Right? In place is nice because you have a very fixed amount, a small fixed amount of extra space that you need to deal with, maybe 1 or 2 extra positions. And being in place means you have to figure out the algorithm so you don't destroy the data that's already there. It's a little trickier in some cases, but we've gone with algorithms that do that. Okay? And remember this, I tried to ask this for everybody who did quicksort on your homework, right? I said, if you did quicksort, why wouldn't you use quicksort for an insertion or for a small data set like 10 or 15 numbers? Why? Because there's all this overhead, right? There's like, partitioning and then sweeping through and all these things that are just taking up too much time. And for such a small array, you're not going to worry about it. You're going to do some other easy sort, like insertion sort. Okay? For your song search, if you're ordering the top 10 songs and those are the only ones you're doing, I wouldn't do a quick sort on that. Right? You can, but it's probably not gaining you anything in that case. Okay? Questions on those? No. All right. So here's some example questions, right? Describe the quick-sorted algorithm. Like, write it out for me. Say, hey, you're going to pick a pivot, and you're going to make sure that all the lower elements in that pivot are on one side, all the upper elements on the other side. Generic kind of terms, right? Explain why divide and conquer algorithms lead to log n behavior. Well, I just kind of went over that, right? Demonstrate how to merge 2 already sorted arrays. If you're doing a merge sort, I could give you 2 arrays that are already sorted themselves, and I want you to show me how you're going to merge them together. Right? And then I might ask you to do a couple iterations of a particular sort, right? Just to show that you can do it. Hey, if I'm doing an insertion sort, what are please, sort the first 3 elements of this and show me how you do each step. Right? I think that's not too much to ask in that sense. Okay. All right, any other questions on sorting? Yeah. Walter. You need to know how to do them, yeah. You need to know them, sure. Yeah, I mean, am I going to ask you to program them? No. But am I going to ask you to describe them? Sure. Yeah. Which kind of goes hand in hand, I suppose, but in the sense of you don't need to, I'm not going to make you program them in that sense. Yeah. Although I've seen finals in this class before where they've done that, so I don't know. I won't make you do that to the extent that it's making you write the code like that. Other questions on this? OK. All right, then we talked about hash tables. And a lot of you have gotten lots of practice over the last few days on hash tables because you're using them in your song search. OK, remember, hash tables in particular are very, very fast because you are in the end using an array that you can index into directly. OK? So you hash a key. How do you hash a key? You use a mathematical formula of some sort. Right? It could be as easy as the mod operation. That wouldn't be a great hash, but it's one that you could do. Right? And then once you have that number, you index it into the array, which holds the data, probably the key as well, in there. And the lookup of the key is the same process, right? You go into you rehash the key, and then you start looking for it. It should be at this location in this index in the table. And then if it's not, well, that's when we get into some other issues. But if you have a hash table that has not too many collisions, which we'll get to in a sec, you can do these operations in one time, which is the best that we're going to get. Okay. All right. So what's the problem? Well, you can only get perfect order 1 if there's no collisions. And collisions are key 1 and key 2 both try to go into that same bucket, right? It was kind of like when I had you guys go around the room, right? And I said, well, go by the decade of your birth. You all over to one side. Why? Because all of your keys collided. Okay, so you're going to have collisions. And we know that we're going to have collisions because there's this birthday problem idea that that you can't come up with a hash, at least it's not easy to come up with a hash that doesn't have a significant number of collisions given a big enough set of keys. It's just not going to happen the way it works, right? 95% chance of at least one collision if you have a 1,000,000 bucket array and only 2,000 hashed values, right? And that's for a pretty good hash. So it's tricky. Okay? You're gonna have to deal with collisions at some point. Okay? Lots of different ways to deal with collisions. Right? We can chain them, which is just simply saying, OK, if two items go into the same bucket, that's fine. List them. Which ones are in this bucket? The following. Boom, 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 boom. It can be an array. It can be a vector. It can be a linked list, whatever you want. But there's no need to worry about the fact that you've got the two items go into the same bucket, because now you say, oh, I'll just make a list of them. I know which ones go in this bucket, and I'm going to search that whole list. That tends to be kind of slow, right? It doesn't. You don't need a new bucket for a key, but the table doesn't have to expand, right? But if you guys think, oh, well, I'm just going to make a table of 100 elements and put 170,000 song, or I don't know, what was it, 30 million unique words, or 300,000 unique words, or whatever, something like that, into a table that's only 100 elements long, sure, it will work fine, for a definition of fine being it will work, right? It's not going to be fast, because all of those chains will end up making it so that you don't, so you have to walk through those whole chains, and that's going to be really slow. Okay? There are other ways to do chains. You could have them sorted some way, and there's lots of ways to do that, but that's not necessarily the best way to do it. Okay, and chaining adds a whole different structure, so you've got to have some other structure there, whether it's an array or a linked list or whatever. And we don't necessarily want to have to deal with that other structure. Okay? Other types of collision handling. Well, where there's this open addressing method, which says, find a bucket. If that bucket's filled, find another bucket to put this one in. And how do you do that? Lots of different ways. The easiest, right, is this idea of doing a linear probe and saying, go to this bucket. Oh, it's not empty. Go to the next one. Oh, it's not empty. Go to the next one. Oh, it's empty there. That's where it's going to go. And just kind of walk along. That actually works fine. And in fact, for the song search, I've got a version that works fairly well, like 2.5 minutes for the whole song search for the big database. And it's using linear probing, right? You do have it's very simple to implement, for definitions of simple. And then the downside, though, is that if you end up having lots of hashes that are going into groups, lots of keys that end up grouping, then you do end up slowing your hash table down, because it's lots of things are trying to go, and then you have to linearly probe away from that as you go. Okay, that's linear probing. What's kind of the next level up? Well, this quadratic probing. Quadratic probing says, OK, fine. Don't step forward by 1. Step forward by some quadratic formula or quadratic polynomial value. And then remember to wrap around. Right? Instead of going to the next one, the next one, the next one, go to the next one, then go to x plus 4, then x plus 9, then x plus 16, x plus 25, and you'll wrap around quicker. You'll spread out the number of hashes faster, the number of locations faster. Okay? Better than non-grouping values. You do have to be a little careful. If you don't watch out, that strategy will lend itself to skipping some whole, lots of buckets in certain ways. And then you won't know if you're going to, you might end up kind of in an endless loop. Okay? All right, what's the next one? Well, double hashing. This one actually works pretty well if you have a good second hash function, because what happens is things are now independent from two keys go to the same bucket. You rehash those keys, and or at least one of them, it will go to another bucket, but then another key comes in, goes to that first bucket, won't go to that second bucket. It'll go to some other bucket, right? And so what you've done is you've now said, oh, I'm going to even spread them out more. So you just double hash and then you keep doing that until you do find the right, or the location that you want. Okay? Lot less likely to have double, secondary collisions. Downside, again, you've got to be careful that you hit every bucket before you expand, right? Or at least hit enough buckets that you don't run into a problem where you're looping continuously. Okay? Hash table, that's the double hash. Okay? Well, sometimes you're going to have to think about how many items are in your hash table, right? So we've got this idea of a load factor, and the load factor says, look, I know how many elements are in my table. I know how big the table is. Divide the two, get this factor that's some percentage, right? Or some decimal number. And when that gets above some value, I chose 0.7 here for my song search. I think it worked great with 0.5, actually. Then you end up having to expand. Okay? What's the problem with expanding? Well, the problem with expanding is that you have to rehash everything. Right? So we'll get to that in the next slide. But the point is, in this case, use this load factor to say, I've got to expand my table at some point. And that point is when you get past some value that you choose, generally empirically. Yeah, Rose?
If you're using chaining, would you ever have to?
No, if you're using chaining, you don't have to expand, right? But if you choose poorly as your table size, at least initially, you'll end up with very poor performance overall, right? Remember, table sizes in general, and I actually didn't do it this way for mine, but in general should probably be, if you're going to use the modding, in many cases you want it to be, your table size to be an actual prime number, right? Because then it does spread it out more across all the buckets, right? Yeah, Vivek.
Couldn't you chain and keep track of how long each chain is, and then expand on that account?
Could you chain and then keep how long? Yeah, keep a list of how long, or keep a number of how long each chain is and expand on that amount. Sure, that's just another way of saying how many items have collided. Sure, you could do that. There's no worries about doing that. It's just another metric you can use. But the idea is, don't slow your table down too much by overpopulating it. Make it expand when it needs to. Okay. All right. So how do we actually go about expanding it? Well, this one, I put a little algorithm on Piazza for the homework 5 about this. But the idea is you have to create another table that's bigger, and then you have to take every element from every key from the first one, rehash it, and throw it into the second one. Okay, so you just basically insert all your current ones into the second one. You can't really get away with that unless you figure out a hash function that leaves the hash numbers the same, or the hash values the same for each subsequent table size increase. But that's hard to do, and I haven't seen it done in practice very well. I think they might do it for some file systems, but that's about it. Okay? This is a slow process. Expanding is not a fast thing because you've got to go through all the elements and rehash them. Now, expanding a dynamic array isn't that fast either. Remember, you're still copying all the elements. In this case, you're doing an extra set of an extra operation and then basically copying it, just copying it to a different position. If you don't rehash, you will lose your values. They aren't going to go to the same bucket anymore, and they're going to be gone. Okay? All right. So that's how we do expanding. Okay. We then talked about cryptographic hashing, right? We talked about this idea that, hey, hashing itself, yeah, and Elaine and I are going to we're going to be business partners doing the our spy agency, right? For cryptographic hashing, you don't actually have to have a table. You basically say, hey, hashes are pretty cool because they're one-way functions. In general, they should be. If they're for cryptographic use anyway, they have to be. Which means that you can go one way and then you can't go backwards very easily. All right? Or in some cases at all. Like you can have many things hashing to one value, so you can't go backwards to find the original. All right? So it's nice because we can use that for digital security, digital signatures. We can use it for electronic commerce. Like all of your purchases on Amazon.com, right? They use cryptographic hashing. Every time you log into the computer, it uses a cryptographic hash because that's the best way we know how to do it right now to keep it as safe as possible. Okay? As far as using cryptographic hashes, well, we already talked about them getting used for passwords. I won't expect you to necessarily know more than, like I won't expect you to apply a cryptographic hash, but you should know a couple of things about them, right? You want it to be easy to compute the hash value. Why is that the case? Well, if you're going to have to do a lot of hashing, you better make it relatively easy to do it. That doesn't mean it has to be fast, right? Because password hashing you want to be slow so that it takes somebody a long time to generate your lots of password guesses so that they can't brute force your passwords. Okay, so sometimes it needs to be slow. We talked about that. But it should be easy to compute it. and easy being not mathematically too rigorous. Okay? You don't want to be able to generate a message that has a given hash. In other words, you don't want to be able to say, oh, this is the hash. Oh, here's the message that created a type of message that created that. Not a good idea, because then you can, if it was too easy to do that, you'd be able to fool the system into thinking that that's the right hash, or that's the right message, and it might not be. And remember, two messages can collide into one hash, but hopefully that's rare. Okay? And you don't want to be able to modify a message without changing the hash. Remember, if you change a message, I gave this example a couple times, if two people have passwords that are like one character off, you want them to have completely different hashes. So you can't say, oh, I know this guy's password and this guy's hash, this person's hash looks pretty similar, I'm going to try a variation of this password. You don't want that to be the case. You want one change to be completely different hash. And lots of cryptographic hash functions will do that. And same thing, you want infeasible to find two different messages with the same hash. That's kind of the whole collision idea. You want it to be infeasible to find collisions. Not possible in the general case, but you can minimize it as you can minimize it. Okay? Questions on cryptographic hashing? I could ask you some questions about that. Nope. All right, so here's some types of questions that we might go over. Well, using the following hash function, not a particularly good one, and a table size of 9, makes it easy, I guess. Hash the following keys, 5, 29, 20, 0, 27, and 18. Right? Use chaining in one example and use linear probing in the other. Right? Do you want to go through that example? To do that? I mean, let's try it. Okay? All right? We may not go through the whole thing, depending on how long it takes. But all right, so you're going to have a table of size 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. OK. All right? And then we are going to do the modulus function. OK, so 5 modulus 9 gives you what? 5 gives you, what is the remainder in this case? Right, 5, right? So hang on, 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's it. All right. OK, so 5, 5. So that would go right here. OK? All right, and then 29. Oh boy, here we go. We've got to do 29 modulus 9. 29, 3, 2, right? 29. OK, and then 20 is going to be 2 as well. OK, so what are we going to do for chaining in this case? We're going to put it down here. So we're going to say, OK, it's 29, but it's also, do this, 3, 4, 5, 6, 7, 8. 8, 0, 1. We'll put all these over here so I can chain them. All right. So it's got 29 and it's got 20 in it. And that's our little linked list. OK, you can have some linked list there to do that. OK, 0 goes to 0. All right. And then 27 also goes to 0. Right. 27. And then 18 also goes to 0. There you go. Done. OK? That's the chaining one. Not too bad. All right. Let's look at it again and do linear probing. OK? Linear probing. So 5. We said that goes into 5. Well, there's nothing there, so we can put it there. And then 29 we said goes into 2. So that's going to be there. Nothing there, so we can do that. 20 also goes into 2. Well, there is something there, right? So we need to go, oh, we got to put it here, 1 over. We check that. Is it there? Is it empty? It is. So we can put it there. 0 goes into 0. There's nothing there. OK. 27 also goes into 0. Well, this one's full, so we can put it here. And then 18 also goes into 0. Full, 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 full over there. And there you go. Questions on that? No, not too bad. I probably wouldn't ask you anything too much more tricky than that, right? Although I might say, OK, walk me through finding 18 in the table now. OK, 18 is supposed to go to 0. Is it there? And you have to check and say, is this 18? No. Is this 18? No. Is this 18? No. Is this 18? No. Is this? Yes. Boop, this is the one. Okay, and you're generally not going to just hash the numbers. You're going to hash the actual, like some value along with it. Okay. Any questions on that? All right. Let's see what else. Write the insert function for a hash table. I might make you actually write this one. Right, that uses quadratic probing with a quadratic probe jump of x squared. Right, the insert function. Same idea as what we just described, except now you're going to jump by that quadratic function. Okay, I would give you a little more scaffolding than that. Okay. And then explain how an element should be deleted in a hash table that uses chaining. So I deleted my example, but if it said 0, 27, 18. If I wanted to delete 27, how would I do it in a chained hash table? Go ahead, Ben. Oh, OK. Yeah, I would just remove it, right? I would just pull it out of there and have the pointer for this one point to the next one down there. Easy enough. Now, in this case, how would I remove, let's say I wanted to remove, what's a good example? 27 in here, right? First I have to do what? Hash 27, find it, right? So I go here, it's not there. I go here, oh, it's here. Can I just remove it? Not in this case, you can't. Right? In this case, you can't particularly because 18 relies on the fact that this one was filled when it got hashed over here. Right? So you have to do something where you mark it as, hey, this was a deleted one. And so you have to check it. Right? Or you could, there's other ways of saying when you find one, move it to the previous location if it's empty and so forth. But you have to kind of keep track of these deletions. Okay? Luckily in song search, nothing gets deleted. All right, let's see, deleted. Any other questions on that? Yes, Ben.
The x in x squared is the attempt, right?
Yeah, I would flesh that out. But yeah, I would say, oh, it's the x is the attempt number, and the first one's going to be 0, and then 1, and then 2, and then 4 squared, or 3 squared, et cetera. Yeah, good. All right, great. So then the last real big topic we had was on graphs. Okay, again, you will see lots of graphs in other classes that you take. Okay, this is one of those ones that it's a data structure, but it's also really, you're going to see a lot of it in algorithms classes and some other classes that you take. Okay, graphs are like trees, except it's like the Wild West, right? There's no structure to it, right? You can't say somebody's a parent and a child. It's kind of ancestral in that sense, right? Right? You just have, it's like everybody points to everybody else, and you can't really tell, and there's no directed structure. Okay? Speaking of directed and undirected graphs, no arrows. Directed graphs say, hey, I can only get from 3 to 10. I can't get from 10 back to 3. Okay. And then you can also have weighted and unweighted graphs where each one of these edges actually has a weight associated with it. That becomes really important when we start talking about the algorithms for shortest path. Okay. Speaking of shortest paths, there's two that we're really concerned about, right? There's one where it's unweighted, and then there's the more general case where it's weighted. The unweighted one is actually just a specific case of the weighted one if they all had weights of 1, right? But we can talk about them, so it's a little easier if you don't have to worry about the fact that there's weights. The second one we call Dijkstra's algorithm, because that's the guy that created it, and it's famous, and you could certainly get asked that lots of times, like for instance in interviews and things. Okay. I'll talk about interviews in a few minutes, actually. OK, so the unweighted shortest path, right? This one basically says, look, find your start vertex. And that's going to be 0. The distance to that one is 0 from itself, right? Find all the ones it points to, and then start adding 1 to those vertices. And if you get to a vertex that already has a lower value than 1 plus your own value, don't change it. Right? Go through all the vertexes like that, and by the end you will have the shortest path to the original, from the original start position to all of the other nodes. Okay? You repeat until all the nodes have minimum distances. Okay? Your GPS does this, by the way. Right? If you tell your GPS, hey, take me to, I don't know, take me to Chicago, right? Well, it finds all, it basically says, OK, I want to get to Chicago, and I've got all these other cities in there. I need to find all the different shortest paths, and it calculates that. Does it do it for every little road in the world? No, of course not. But it does it to a first approximation for many of the routes that you could travel on, right? And one of the problems with Google, it actually does a great job, but sometimes it doesn't know about traffic, and sometimes it doesn't know about like road closures, and sometimes it just doesn't know some of these things. So it can give you bad information, but for the most part, it does pretty good. Okay. All right, let's see. I think, yeah, this is the one. So we look for vertices at the distance of 1. Sorry, start at v3. This is exactly the same as the previous one we did. And then you go to this one, and then this one, it becomes 2 to there and 2 to there, because those are the only ones that vertex 1 points to. And then you go to 2 and 2. This one becomes 3. And this one you don't change. It would become 3, but it's already 2, so you don't change it. Then you go to this one, and let's see. Oops. I guess I didn't fit. Oh, it was all done. There we go. Because you go to this one, and this one, this one changed this one, and I forgot to go to this one first. That this one doesn't actually change anybody else. This one changed this one, this one. This one finally changes this one. So you can, the unweighted case is a pretty simple one to do. Okay. And then finally, we had Dijkstra's algorithm. And I'll go over this one more time with you, right? Dijkstra's algorithm says the following. It says, look, again, it's in stages. It's a greedy algorithm. And it says, do what's best right now. And whatever I know right now, I can go ahead and do. Right? So if I'm starting at, this time we're going to start at vertex 1. Okay? And it says, let's see. Oh, did I actually leave the, hang on. Oh, there we go. OK. So remember, we can have this table that goes along with it to say, OK, look, from here, the only one that we know that's at a distance 0 is the first one. Everybody else is, as far as we know, a distance of infinity. Right? Everybody's at a distance of infinity. And then you go along and you say, OK, look, who can I reach? So who can vertex 1 reach? It can reach 2, and it can reach 4. Right? And it knows the distance, so it adds its distance, 0, to 2 and to 4, and then puts that in the table, which is right there. Right? 2 and 4 gets, the 1 to 2 is 2, and the 1 to 4 is a distance of 1. And now those ones have minimum distances. Right? What you do now is you say, which one of the ones I haven't marked as done yet, and I just marked the first one as done, which of the ones that I haven't marked as done yet is the smallest? Well, in this case, right, the smallest is vertex 4. So we have to go to vertex 4. Right? And so we go to 4, and we say, OK, who can vertex 4 get to? Vertex 4 can get to 7, and it can get to 6, and it can get to 3. So we update all those. Right? And by updating, we add its current amount, which is 1, plus the weight to get to that one. So vertex 4 to vertex 7 is going to be plus another 4. So we would say that's going to be 5. And vertex 4 to 6 is going to be plus another 8. So that's 9 total. And vertex 4 to 3 is going to be 1 plus, so it's going to be 3. Vertex 3 is 3. And now those are all set up. So look, we've now actually marked everybody as having some value that's not infinity, meaning we can get everywhere. And then we say, now we say, OK, let's go on to the next one that hasn't been checked yet. That's the least. There's a 2 there, a 3 there, a 3 there, a 9 there, and a 5 there. So we have to go to vertex 2, et cetera, et cetera. Okay. Vertex 2. And we mark vertex 2 as known. And we don't need to just 5 because 5 already has a value that's based on 4. So if we went to 2 and 2 says, look, I can point to 4 and I can point to 5. So if I tried to update with 4 with a value of 5, it's not going to work. And it doesn't, where you shouldn't do that. And the same thing with 5. Let's see, 2 plus 10 is 12, but 12 is bigger than the 3 already at 5, so you don't update that one. Okay? The algorithm's relatively straightforward once you understand it. Right? And by the way, we're keeping track of the previous, the one that we actually used to set that value so that later we can go back and find the route. Okay? It would be a bad idea if Google Maps said, OK, to get to Chicago, the shortest time is going to be 16 hours of driving. And you go, thanks? Right? I mean, like, it doesn't tell you how to get there. That would be bad. Right? It could tell you, oh, it's going to be this far, but not tell you how. You got to keep some idea of where you've been so that you can walk back and see that later. Okay? All right, when you have ties, in this case, let's see. Well, we actually picked 3. So when you've had ties between 3 and 5, you can choose. Your algorithm should just choose one of them. right? And we chose 3, and so we look at 3, and 3 can go to 1, but that's already done. And 3 can go to 6, and that's going to actually get modified, right? Because it was 8, and now it's going to be now it's going to be 8. And before it was 9, okay, etc. Okay. And then we can do 5, and then we can do 7, and the last one we have is 6, and then we can do 6, and we are complete. Okay. How do you figure out what the shortest path is? Like not the amount, but the shortest path. If I want to get to 7, well, I start at 7. I say, what was my previous one? It was 4. So I go 4. What was 4's previous? 4's previous was 1, and I'm back to the start. And that's how you get there. And just reverse it. You go 1 to 4 to 7 to get there. All right. Anybody have any questions on that? How Dijkstra's algorithm works? No? OK. You should be able to do that for the test. OK. All right. So what are some questions I could ask you about graphs? Well, I could say, hey, do an adjacency matrix. I didn't really mention that today, but write out the adjacency matrix. You should have done that in lab, actually, where you practiced doing an adjacency matrix based on a graph. Okay? And I could give you a directed or an undirected graph for that. You should also be able to do an adjacency list, which would basically say, here's a vertex. What vertexes can it get to? And then the next one, what vertexes can it get to, et cetera. You should be able to do the breadth first or depth first traversal. In other words, starting at a vertex, give me a complete depth first traversal of that, right? And depth first means go to the next one, and then go to its vertexes that's adjacencies, and then go back, and then backtrack as you need to. That would be depth first, right? Breadth first says kind of go out to all the ones that you can touch individually, all the ones you're adjacent to individually, and then go down that path. Dijkstra's is a, well, what do you think? Is Dijkstra's a breadth first search or not? It's a greedy algorithm, but is it necessarily depth first? Not necessarily. I don't think it's necessarily either, to tell you the truth, right? Because it depends on what the weights are as to whether or not you're going to go one path or the other, not just whether you're adjacent to them. Yeah, good. OK. And then find the shortest path. And by find the shortest path, I don't mean like, oh, it's that. I mean like, show me how you got that step, right? For an unweighted graph, or apply Dijkstra's for it. OK. All right, good. All right, so I guess go back there. That's it for the stuff that's going to be on the final exam, right? I mean, it doesn't seem like quite as much maybe as the first semester. I mean, I think there's a lot. We put a lot in there. Obviously, you'll have to know something about the previous stuff because it all builds on itself. But again, I won't specifically say how does a queue work or show me how a stack works because we already covered all that stuff. Okay, mainly going to be focused on the stuff we talked about today. Okay. All right, good. Okay, so I wanted to go back to day 1. I don't know if you remember this, but if it's OK if you don't, I told you didn't have to really. I just wanted you to kind of understand the overall idea. I mentioned a couple of 4 different types of structures, right? And I said, hey, there's this thing called a dynamic array. Then I said there's this thing called a linked list, and you might have heard about those. There's this thing called a hash table, and you probably never heard about that, but now you have, right? Woohoo. There's this thing called a binary search tree, which you also at that point may not have heard of. Okay, and I said, hey, I'm going to do the following operations on some integers in those structures. Okay, for each of those containers, I'm going to take 100,000 elements, and I'm going to add them to the containers. And in fact, the particular 100,000 I'm going to add is 0 to 200,000, skipping just the evens, basically, just doing the evens. Right? 0, then 2, then 4, then 6, et cetera, and sticking those in our 100,000 element structure. And then I'm going to go and search for 50,000 of them. In fact, I'm going to search for the numbers 0 through 50,000. Right? Half of them will not exist in that structure because I only put the evens in there. And then I said I'll go and delete 20,000. Right? And back then you might not have been thinking, oh, delete, that's easy. Right now you're like, oh no, if I have to delete out of a linked list or if I have to delete out of an array, I have to go and move all these things around, right? OK, so now you kind of understand some of that stuff. But anyway, that's what I showed you we were going to do. And here were the results. OK, All right, so for the array, the dynamic array, we had insert, search, and deletes. Okay, dynamic array did fairly well, but it took about a little less than 2 seconds. Linked list was kind of horrible, right? It was 8 seconds. Hash table, though, right? And I said, don't worry about this, we'll get to it. But now I hope you guys understand why a hash table actually has such great performance, right? Everything's ON, or order 1, really, right? You do all this stuff so fast because it's a hash table, and you can do all these things. You can insert, you can delete, you can search for things very, very quickly. Aha, now we know a little bit about that. Binary search tree, also pretty good, not quite as good as a hash table. Why? Well, it's logarithmic, right? And you guys know that now. There's all these logs in there. But logs is better than linear, which is better than n squared, et cetera. Then I threw in this sorted array. And I said, oh, I got a sorted array in here. What's all that about? Well, this one, they were all sorted, by the way, because we put them in there sorted. But I knew that this one was sorted, and I knew that I knew it was sorted. So I was able to do binary searches on it, right? So inserts, I don't know if you remember me saying this. This should be the same as this, but it has to do with caching. There was some caching effect in there, saying I already did this basically for the same set of the same array. So it's going to take much less time this time because that data is already kind of in the cache, as it turns out. But these should be roughly the same anyway. And then searching, though, very fast, right? Why? When you search through a sorted list, how can you search? If you reach a number that's greater than the one you're looking for, okay, that is one possibility. But remember, if it's sorted and we've given you the information that it's sorted, 0, 8, 23, 40, 70, and 100, right? If I know I'm looking for a number between 0 and 100, or it doesn't even matter, right? If I'm looking for the number 7, do I start at one side? No, where do I start? In the middle, right? Because this is the divide and conquer thing, right? So I say 23. Now I can say, oh, it's less than 27 is less than 23. I could care less about that half. I've chopped the problem exactly in half, right? And then this one I go halfway again. It happens to be right there, so we're good. But I've chopped the problem in half. And so it's not just that you can stop when you get past something. That would be a linear search. Well, not even a linear search. If it's unsorted, you have no idea. But for a sorted list, do a binary search and you're good to go. So that's what I told for the sorted array. I said, don't just use your linear search. Use a binary search because I know it's sorted and you'll get the right answer, right? So we did that. Okay, and the searches were really fast. Okay, cool, huh? So this morning, I said, well, all right, can we do a little bit more comparison on this? And hopefully, by the way, in your debrief for your in-person grading, or in your in-person grading, you saw the graphs or the tables. And if you haven't done it yet, you will. But you get to see the actual effect that an n-squared algorithm for your selection sort has on the data, right? If you have 10 times more data to sort for a merge or for a selection sort, it takes 100 times more time to do it because it's an n-squared sort. Okay? So what I said was, all right, look, these were 100,000 for all this. What happens if I do 1,000,000 for all this? Right? Well, my computer's fans came on. Let me put it that way. Right? So for the array, 163 seconds. For the linked list, 1,047 seconds. Like it just sat there for however long that is, right? 15 minutes or whatever. Right? And did it, right? That's because the searches took forever in the linked list. Not a good thing to search for. Okay? Hash table, though, look. Hash table went from, I'll show you the overall in a sec, but it's still 0.01, still a 100th of a second to do all those searches through 1,000,000 of them. Right? That's awesome. Binary search tree, also still very fast. Sorted array, also still very fast for searches. Okay? Not so great for deletes, though, because you have to search, then you have to move, you have to delete and move everybody. But here's the actual results here, the comparisons here. All right? This one went from 1.6 to 163. Aha. Now, this is a little harder to analyze than the sorting. But how many times slower is it? 100 times slower than it, right? It's not that we've got some n-squared behavior for say, searching or whatever, right? What it is it's linear behavior, but it's times 10, like 10 times more things that you're actually searching. So you're doing 10 times more work, right? And it's taking 100 times longer because it's linear per element. That's really what the big one is there, right? So forget the linked list for 1 sec. Let's go down the hash table. It goes from 0.01 to 0.12 for the overall, right? It's about 10 times slower, but you're doing 10 times as much work, right? That means it's a constant for each one, right? You do have to do 10 times more work, but you have to do 10 times more work, and you only have to spend 10 times more time doing it, meaning there's no difference in the order of each operation. Binary search tree, this one's a little weird. I think this should actually, it might be doing something extra under the covers that I don't know about, but it's about 10 times, is it 10? I think it should be a little bit slower actually based on the fact that it's log n behavior for each one, but it's still, you can tell it's still relatively fast. And the sorted array is weird because again you have to do the deletes, right? Let's go into a little more detail. Here. For the inserts, okay, takes about roughly 10 times more to insert 10 times more elements because they're all constant inserts. Linked list, about the same, about 10 times more time to insert into a linked list. Hash table, let's see, about 10 times more because you have to do that. So these are all order 1 operations, right? Binary search tree definitely takes longer because this is a log operation. And a sorted array, also about 10 times longer, but we've got the caching involved there, inserts. This is the one that's kind of interesting, though. Searching. Array, to search through an array, if you have to do it linear search, you're going to have to go through 10 times more stuff for each element, right, in general. Right? So it's going to take 100 times longer. Linked list, 100 times longer. Right? More than 100 times in this case. Yeah, question?
It's kind of related to this, but it's also on the homework.
Yeah.
Do you think something that's like a sorted, using like a standard template or a library,
Yep.
does it know that it's sorted if it's like doing something?
Does the standard template library know that it's sorted? In a vector, no, unless you sort it. What's that?
In like a multi-set or like
Yes, in a set or a multi-set, it knows that it's sorted. Yes, it's using a tree under the covers,
Okay.
using a binary search tree under the covers. Yep, yep. And then the sorted array, this is the one where we can now say, hey, look, we are, we can do a binary search on this, right? And so in this case, this is another weird one. I think it's doing something funny under the covers as far as searching a little bit faster. It might be, the way the standard library works, it's like, look, if you can do it faster as long as you're right. And so under the covers, even though I say do a binary search, it might be able to search like 2 paths at once based on something. So it might be doing a little funky thing. But the idea is that you can tell arrays are terrible behavior, linked lists, even worse behavior, right? Hash tables, awesome behavior. Binary search tables, very good behavior. And sorted arrays, very good behavior for doing the searches. Okay, and now you guys should be able to analyze this stuff. And I think at this point, you're to the point where you can do those analyses much better than you were on day 1. Okay, so congrats on learning all that. All right, finally. So we didn't cover some things in this class, obviously, right? The class isn't like 6 years long, right? There are thousands of different data structures that you will find out through your career. You have the basic ones, right? You know the base models for all these things. Okay, if you know what a tree is, and you know trees have nodes, and you know how to deal with trees. But there's also splay trees, right? And there's something called an oct tree, and there's a KD tree, and a radix tree, and all these things that are derivatives of kind of a basic tree, right? There are maps, different types of hash tables, right? Different types of maps, different types of heaps. There's a thing called a 2-3 heap, right? Or there's things called, let's see, well, B tree is a different type of tree. I don't think I put another kind of heap on there. There's a Fibonacci heap, which are other types of heaps, right? And so they're all just derivatives. If you know what a heap is, you can go, okay, Fibonacci heap. Well, I guess I better figure out what that is. These are people doing research on this stuff and coming up with new data structures, right? And sometimes those data structures work better than the data structures that the base model, right? I mean, they have a different type of engine in them than the base model, right? They have a different way of doing things. If you want to merge 2 heaps, right? merging heaps is not easy, actually, right? The easiest way to merge a heap in general is to like just remove min from one and insert into the other. It's not particularly fast, right? If you take another kind of heap called a like Fibonacci heap, right, or a I think the 2-3 heap may be like this, right? Or there's another one called a leftist heap, right? The leftist heap kind of keeps everything to the left if it can, right? And it turns out that if you do that, merging two leftist heaps is a matter of combining the root. Like it's that easy, right? So depending on your use cases, you are going to want to pick some other different specialized data structure. But the idea is you now know how to analyze data structures, you now know the base models of these data structures, and you now know how to actually go about like programming some of these. And you know under the covers. And one of the things about this homework assignment is knowing under the covers is not or knowing what's going on under the covers is important in many cases to pick a data structure. So if you're using the standard library, you kind of want to know what it is under the covers so that you can pick a fast one, right? Don't pick some sort of list if you know you're going to be doing lots of searching through it. It's just not a very good structure to do that, and you know that now. I have no idea what a spaghetti stack is, right? But it's in a big list of data structures. Okay? The idea, always use the best data structure for your task. Why? Because you know what your task is, and while I'm thinking about it, who's actually interviewed for tech jobs so far? Sam, I know you have. A couple other people, right? Yeah, I know you have, David. Did they ask you any data structures questions in yours? No. Yours a little bit. If you get a job if you go to Google, for instance, and on day one, I think I said Google, this class is like the how to interview for Google type class. They will almost certainly ask you something about the basic types of data structures, right? They may throw you for a loop and say, hey, there's this thing called a 2-3 heap, right? Blah, blah, blah. One of the TAs, Ashley, I don't know if you know Ashley, she had an interview where they asked her about a trie, and she hadn't done tries in her data structures class, but she figured it out. I mean, she said, they walked me through what it was, and I thought about it, and I figured it out. But she knew what a tree was, so she could kind of think it through. But the idea is, why do tech companies ask you about data structures? Well, they need you to know about efficiency. They need you to know about what types of structures are going to behave best for your system, right? I mean, if someone came into Google and said, hey, I want to redesign your search algorithm to use linked lists, right? They'd be shown the door, right? The guy, I just found out about this cool thing called a linked list, and I want to use it for you. I think you need to use that, right? They'd be like, thank you, no, right? We're all about hash tables or whatever they use there, right? Tries or whatever. But it's the reason they ask about this is because this stuff really is fundamental, more so than just the programming. You need to know how to program, but you also need to know the fundamental like data structures and how those behave. Okay? Questions on that? You guys next summer or next spring might want to think about if you're looking at doing interviews and so forth. Go back to some of the notes we've done and kind of refresh your memory on that so that you keep up to speed on the types of questions they might ask you. In the references section here, I do list some various stuff that you can look at. List of data structures. There's lots of them, right? Lots of questions that people might ask. I may use some of these on the final. You never know, right? So if you go and like kind of browse through some of these questions. Why are data structures so important in interviews? That's in there. And more on data structures. Okay? All right. So that pretty much leads us to the end of the semester. This is my first semester here at Tufts. I appreciate you bearing with my mistakes. I apologize for some of the mistakes that I made during the course. For what it's worth, and this doesn't help you necessarily, but I hope to do a little better next semester for those people. So you can say you can lament to them next semester and say you're getting it better because he had all that practice on us. So I do appreciate your hard work in here. You guys, I've seen lots of you guys they're working really hard on the last assignment, and I appreciate that. It is a hard assignment, so I will take that into consideration, obviously, when we're doing the grading. OK, any other questions before I let you go? There are labs today, by the way. I will find out where the final is going to be. I expect it to be in here, but I don't know yet. Okay. Other questions? All right, thank you very much. Thanks. Oh, thanks. Thanks, guys.